All right, so I've only got, 15 minutes, so let's go through this pretty quickly. Thank everyone for being here. I'm going to be talking today about some development strategies we used in creating this package called SparseBN. So what is SparseBN? It's our package for learning large-scale graphical models and complex networks from data. The motivation for this came from computational biology, where you have very high-dimensional problems where, we'd say P is much larger than N, so you have many more variables than you have samples. So basically what differentiates this package from many of the existing packages in the R ecosystem is it's very fast, it's built upon RCPP, scalable, built for very large networks with tens of thousands of variables. And for the statisticians out there, you'll be happy to know that this is one of the few packages that actually comes with solid high-dimensional statistical theory for learning these types of graphical models. So let me just give a quick overview. So I'm going to talk mostly about how we built this package, but just so everyone's sort of on the same page, what this package does. Like I said, it's much faster than existing methods. You can do graphs with about 5,000 nodes in a little over a minute. If you have mixed observational experimental data, this was built into the package. So this is very helpful for biologists that typically have, say, gene knockout experiments or various types of interventions that they'd like to deal with. And then the main features, it does structure learning, parameter estimation, model selection, visualization, sort of all of the standard pieces of your statistical framework. And then finally, one of the sort of challenging aspects that this framework we sort of built to help with is to make it compatible with the existing R packages. So this includes other R packages for structure learning, and as well as various graph packages like iGraph, network, et cetera. So you can use your favorite graph class in manipulating the graphs that come out of this package. And then in the pipeline for anyone who may be using this package or is curious where we're going with this, so there's a lot of sugar that we want to add on top of this. Things like blacklists, whitelists. Biologists are probably familiar with the application Cytoscape for doing network exploration, so we're working on adding a link to that and various methods for network comparison and evaluation. Those features, like I said, are just kind of sugar. They're just meant to make things easier to use. What we're really interested in and what I want to talk more about today is how we're making it easy to add faster algorithms. So faster algorithms for bigger graphs and also adding different types of statistical models. So right now we have models for Gaussian continuous data as well as discrete data, but we're interested in adding in new models for, say, count data using, maybe a Poisson model and various forms of generalized linear models. So basically, this framework was developed to make it really easy to plug in new methods from future developers. So just real quick to show you, you can take 5 lines to get yourself a DAG. So really, in these 5 lines, we're doing 4 things. We're loading the library down here, and then we load the data, and then we have this function right here, estimate.dag, that does exactly what it sounds like. It estimates a DAG. So a DAG is a directed acyclic graph. Don't worry if you don't know the details of that. It's not really important for this talk. And then finally, we can go ahead and plot, and we'll see some of the networks that come out of the estimation procedure here. So a lot of effort went into making this code, which does a lot of things, very simple. And in particular, the estimation function is essentially a black box that just takes in your data and sort of magically spits out networks. And that's sort of the idea behind this package. So let's talk about some of the challenges to sort of motivate why we needed some new development strategies for this. So I'm not going to go into the mathematical details. We have several papers on this. If anyone wants to, I'll have references at the end for those of you who are curious. We can also talk offline if you'd like. But basically, all of these methods boil down to this really nasty, non-convex, non-smooth combinatorial optimization problem. And the long story short is that you can't just throw something like gradient descent, proximal methods, splitting methods, any of the standard optimization schemes. They're not going to work on a problem like this. So we needed customized optimization algorithms. However, each of these optimization algorithms is different depending on the type of data you have, the statistical model you're using, the objective function, the regularizer, and lots of other things. So this isn't really new. There are a lot of R packages that deal with these types of issues, say for mixture models, regression models, et cetera. What made this package sort of different, and what I think makes it sort of interesting, particularly for academics, is that we were working on untested, unstable, and frequently changing algorithms. And what I mean by this is what's on CRAN is a stable, tested algorithm, but when we were implementing this, we were taking new ideas that were sort of at the research level and sort of playing around, and we wanted essentially a software framework that allowed us to do things like rapid prototyping, enable fast release cycles, and make it particularly really easy to add new methods. So we have an idea, we want to test it. If it doesn't work, it never sees the light of day. If it works, then it's on CRAN, and we want to make that as easy to do as possible. So those are the technical software challenges we had to deal with, but there's also some very human challenges that you have to deal with. Any of you who've worked on a dev team can probably relate to what I'm going to be talking about here. So let's suppose we have a hypothetical dev team here. So if you're in academia, you have a principal investigator. If you're in industry, you have some sort of team leader. Let's call her Susie. And then we have Jane and Bob, our senior dev and our junior dev. And then depending on the size of your team, you might have more or fewer. And here's the sort of setting that we had to deal with and that many other teams have to deal with. So Susie, the leader, has this idea for a fancy new R package. It implements some pretty cutting edge ideas. So things are sort of untested. There's sort of this new little playground we want to use. Jane, the senior developer, has spent several months developing this package. And so she's optimized the code. She's thought very deeply about this. She has a particular application in mind. Bob comes along, say he's a PhD student, so his dissertation topic is to, say, implement one of the count models that I mentioned. So he takes Jane's code base, and it's very well written, but he realizes, well, Jane wasn't thinking about count models when she wrote this, so he's going to have to start tweaking things. So Jane and Bob start working together, and Bob gets going, but then eventually the inevitable happens. Jane leaves, and Bob is left to cry. So the question is, how do you deal with this type of scenario in either an academic or an industry environment? And that's basically what I want to talk about here today. Okay, so here are the two solutions that at least I've seen more often than not in practice. So the first is that, so in order to get rid of these issues of having people dealing with Bob relying on Jane, you have each programmer develop their own independent package. This is very flexible. Each programmer gets to do whatever they want. It's embarrassingly parallelizable. The cons, of course, software devs out there are cringing right now because you have a lot of duplicated code and very lengthy dev cycles, right? So this isn't the most efficient way to do things. And at the end of the day, Bob is just going to rewrite and refactor most of Jane's code, right? This is what happens in practice. The alternative to this, and I think, correct me if I'm wrong, but this tends to be more popular in the R ecosystem, is that you develop one sort of massive monolithic package that does everything and everyone works on this together. So here you have minimal duplication, you have very efficient code, but now the human challenges come in, right? So there's less flexibility, maintenance and upgrades are very costly, and the development process is coupled. And any of you who've done this before, you know that at the end of the day, Bob is still going to rewrite and refactor most of Jane's code. So you still have this issue. So the question that we sort of posed to ourselves when we were developing this package is there some sort of in-between, just-right Goldilocks solution that gets you sort of the best of both worlds? Still going to be some disadvantages, of course, but can you kind of interpolate in between these two extremes to get something better? And so without bearing the lead too much, here's how we designed the sparse BN package. So I'll go into this dependency map a little more detail on the next slide, but just to give you an idea, over here on the left, these are all our external dependencies. So BN learns, another package for structure learning, iGraph, graph, network. These are packages for manipulating graphs. And then here in the middle, we have the sparse BN utils package. So this is a workhorse package that basically defines an interface for the rest of these packages, and I'll talk more about that on the next slide. On the far right, you have the sparse BN package. So if you've downloaded this package, which you should all do right now if you can, this package literally just loads the dependencies. It basically does nothing but load all of these things. And then here, CCDR algorithm and discrete CD algorithm are two packages that implement the actual algorithms, the actual research code. So there's nothing publishable here, okay? This is just a lot of glue code. This is the stuff that's publishable. This is the new stuff that's sort of interesting. And the most important thing is that what sparse BN utils does, in addition to defining a lot of common code and classes, is that it defines an interface that the algorithm packages are going to have to adopt, okay? So sparse BN utils tells these packages what the input has to be and what the output has to be, and so when a new dev comes along, they don't have to know anything about the internals of this package, okay, which supports them. They're going to use it, but they don't really need to know anything about it. They're just going to focus on what the input is and what the output is, and then they get to go to town, okay? So let's abstract this away a little bit. So you're making your own R package. You've been inspired by me here, and so you have something that looks like this. The base package, so this would have been sparse BN utils. This is your workhorse, okay? So this defines all your common classes, subroutines, utilities, glue code, all of that. So you want to think very carefully in advance about what is common in your package that everything is going to have to use, so all your classes and whatnot. And it's also, like I mentioned before, it's going to define the input-output for your algorithm packages. So all of these models here, all of these different algorithms are going to rely on whatever the input-output interface defined by your base packages is. And this is going to be a collaboratively maintained package. Everyone is going to work together on this. So there's a little bit of that monolithic flavor in this package, but we'll see the advantages down here. So the algorithm packages, these implement the different algorithms, and these are independently maintained. So in theory, the different devs can work completely independently and never communicate with each other and develop their own packages. So you get that embarrassingly parallelizable style that's really efficient. Hopefully in practice the devs actually do communicate with each other. That would be great. But so you have a little bit of this monolithic approach up here, but it has the advantage of allowing very quick development of new packages down the road. And so when we're talking about, say, implementing a count model, the hard part in doing that is the research. And once we figure out the right way to do that, it's actually going to be really easy to go ahead and plug in a new package for that. And then finally, we have the wrapper package on the right, and this is just to make things easy for the users. They don't have, most of the people who use sparse BN don't have any idea that there's any of this nonsense going on over here, right? They just look at this package, and all it does is load the dependencies for them. All of the functionality should live inside your dependencies. The one exception to this, if you do look at, if you're interested, you can look at the code on GitHub for sparse BN. There's a few wrapper methods that I've defined to just to provide a nice user interface for the users. But other than that, it really doesn't do anything. It's just loading a bunch of dependencies. So this is sort of the rough outline that we used. Let me just talk a little bit about what some of the advantages and disadvantages that sort of we noticed when working on this. The main advantages, so the first is you get independent asynchronous development. Bob is no longer reliant on Jane, so when Jane leaves, it doesn't matter. Bob can still work on developing his package because all he has to worry about is what the input-output is, okay? So you get that advantage. You get rapid prototyping, so this is a huge deal for us, okay? We want to be able to release new ideas as soon as possible, and we also want to be able to filter out good and bad ideas. So there are several packages that have never seen the light of day because I tried something and it didn't work. But it was really easy for me to do that as a researcher because we'd put in the legwork in the sparse BN utils package to make this happen. And then finally, this is a very flexible workflow that works very well with devs of different skill levels and various levels of seniority. And one of the nice things is the model packages can mature at their own pace. So junior devs don't have to get in touch with the senior devs to say, I'm going to release a new version of the package. They just do it because they're sort of in charge of that and they get ownership over their own package. Disadvantages, I'm biased. We used this, it worked really well. I didn't really see very many disadvantages. One that I will mention, CRAN submission does take a bit longer because now instead of submitting one package, you have 4 packages to submit. There's that, but it's, in practice it doesn't seem to be that big of an issue. Other than that, I couldn't really think of anything. I have to have multiple RStudio windows open at the same time. I don't know if that's really an issue, but I was just trying to think of something. This system seems to work really well. I'm running out of time, so I'm just going to stop here. I just want to thank all of the amazing developers who've worked with me on this package. If you are interested in joining, please submit a pull request. Everything is open source and available on GitHub. And in case you're curious in learning more about the sparse BN package, which I sort of glossed over really quickly, we have a paper on the archive that goes into like all the details you could possibly want to know about the package. So that's available there, and I'm going to stop there so I don't go over time. Thank you very much.